Hello. Here we are going to be discussing the oscillatory response of a gel to wave-induced velocity gradients in the context of marine oil spill remediation. I'm Richard, and while I now work for Golder Associates, this research was completed in contribution to my graduate thesis under the supervision of Dr. Greg Lawrence at UBC. This research was funded by BC Research, MITAX, and NSERC. BC Research is a private research organization currently developing gels for use in oil spill remediation. Now, without further ado, let us begin. Oil spills are bad news. Release of such toxic substances spells disaster for most ecosystems. Spills are and always will be a risk associated with the continued and currently still increasing global demand for oil products. While oil transport is getting safer, large spills can and do happen. And, in part because an oil spill is a continually evolving system, cleanup is particularly difficult. One category of rapid response chemical showing some promise in spill response is that of gellants, a class of solidifier. Solidifiers are chemicals that make a spill more solid. This can render a spill weatherproof, preventing the oil from spreading or emulsifying, processes which make remediation more challenging. There are many types of solidifier, but most require uneconomic amounts of chemical to solidify the oil. Gellants, particularly low molecular weight organogelators, may require considerably less material to solidify the spill, and might even permit the reuse of both oil and gellant. Gellants work by forming a molecular lattice through the liquid oil, giving it a coherent structure. Unfortunately, there is very little literature on how gels might interact with the marine environment. For instance, how might a marine surface gel interact with a linear surface gravity wave? While bending will undoubtedly play a role in gel breakage, we will be considering a different mechanism. Water particles in a linear wave move in closed orbits. At the wave crest, motion is with the wave, and at the wave trough, motion is against the wave. This means that relative to our undrifting gel on the water surface, we have a horizontally non-uniform water particle velocity distribution. This spatial velocity gradient, periodic in space with the wave, will induce a horizontally non-uniform shear stress next to the gel, which can be modeled using the solution to Stokes' second problem. A non-uniform shear stress results in a gradient in tension along the length of the gel. This tension could potentially lead to gel breakage. Experiments were designed to take advantage of the depth-linked vertical decay of linear wave particle orbits to subject a dense model gel to a horizontal spatial velocity gradient without worrying about bending effects. The model gel, gelatin, was placed at the bottom of the 3.3 meter UBC wave tank and constrained vertically using a mesh. A variety of gel lengths were tested for a range of wave parameters. A 4 mm crack was initialized at the mid-length of each gel to ensure consistency of breakage. Gel behavior was videoed and strain results calculated using image analysis. Gels, neither truly solid nor liquid, are instead labeled as viscoelastic materials. The two most basic viscoelastic models are the Kelvin-Voigt and Maxwell models, consisting of springs and dashpots in parallel and series respectively. The forcing term most important for net gel stretching is the average tensile stress, the integral of the stress equation we saw earlier. The result of this sinusoidal forcing term should be a sinusoidal strain response, predictable using these derived equations. As expected, we observed a roughly sinusoidal strain signal in each of the gel samples. For the longer samples, this resulted in complete breakage by crack extension. Unfortunately, the strain seen in experiments was considerably larger than predicted, even accounting for both exposed sides of the gel. Interestingly, the degree of underprediction was of fairly constant proportion. The one outlier here had significant interaction with the mesh. This constant correction factor suggests that another force, such as that on the blunt ends of the gel, could be playing an important role. Applying the stress correction factor for the central cross-section of the gel, we see that the gel only broke when stress exceeded 7 pascals, significantly less than the yield stress of the material, 35 pascals, and at a level achievable by ocean waves. It is certainly enough evidence to inspire future research into this area. Researchers should consider accounting for additional forces, looking at a wider range of gels, and validating results on the water surface. That brings us to the end of our presentation. Thank you very much for listening.